Welcome back to my channel. With the Tipping Point game just announced, every Vex team from all around the world will be making a plethora of design decisions to get those funny shapes into the goals and get their robots on the balance. And whether they use a claw or a flywheel, the robots will need to move around. So one of the first design decisions will be the base, specifically which base to use. So what this video attempts to do is give some reference numbers so Vex teams can make informed decisions. How much faster is one drive compared to another? The answer to this question will be applicable to all facets of Vex, but especially in skills, where time is a valuable commodity. Another question is, how much can one drive push around another? This may be useful to know for the tournament aspect of the competition. Lastly, and less straightforwardly, this video looks at turning. First, we'll go through the drives. There are many iterations of these drives, varying gear ratios, changing the center of gravity, etc., but we've made each drive as basic as possible so that useful baseline information can be gleaned to specific questions. Here we have two standard drives with 4-inch Omni wheels. These will be tested with 2 motors and 4 motors. Next, we have the H drive. Here we have a drive with Mecanum wheels. And lastly, we have a holonomic or X drive. Here are the weights of all the drives tested. No matter how good your design is, if it takes too long to get around the field, the robot has a lesser chance of doing well. The standard tank drive with 4-inch Omni wheels went 3.36 feet per second. This represents 1.02 meters per second. A quick side note, all the numbers can be seen on this graph, and from this point onwards I will mention the percentage difference. We can see if we drop 2 motors from the standard tank, we get minimal decrease in speed. The drop-off is only 3.3% slower. Not a large drop-off for getting 2 more motors to execute other objectives, but that's up to you. The H drive was 3.4% slower than the standard drive, so for an extra motor, you get the ability to move sideways. The Mecanum-based chassis is 4.6% slower than the standard tank drive with Omni wheels. So here, for the same amount of motors, you get the freedom of movement in all directions and a small drop-off in speed. The small drop-off in speed is likely due to increased friction in Mecanum wheels and that some of the motive force is directed inwards or outwards depending on the alignment of the wheel. The X drive is 17% faster. This is significant. However, interestingly enough, by the physics of the drives, one would expect the speed of the X drive to be even faster. Specifically 41% faster. Since some of the drives can strafe, we also measured the lateral speed. The X drive really shined in this comparison because it went 1.3% faster than when it was going forward, the number for all intents being the same as predicted. The Mecanum drive had a drop-off from its forward motion of 5%, and compared to the X drive, the Mecanum drive was 76.1% the speed of the X drive going laterally. The H drive did poorly going laterally and was only 20.4% the speed of the X drive. So the X drive was 5 times faster than the H drive in the lateral direction. But before we go into why, let's first explain how we got the numbers, to provide context for these findings, offer a way for others to attempt to reproduce the numbers, and see if there were any faults in these methods. So what we did is have each drive complete 10 runs in a Vex field. The robot, which is simply a drive in 10 pounds, would start with one edge against the side. When the program was executed, the robot would drive 108 inches, about the width of the field, and then stop when a line following or detector sensed a line. Then the robot would turn around, be situated, then execute another run. The program would record the time from beginning until the line was sensed. New batteries were used for each drive set of 10. This method took out the tedious and error-prone measuring of distance and made time as measured internally by the V5 brain the only variable. The runs were repeated 10 times and stored on an SD card, then downloaded and analyzed. Next, let's take a look at force. If pushing other robots around is your goal, provided you're not being pushed from the side, a standard tank drive with Omni wheels is significantly more powerful than the other drives. Here are the numbers. Starting with the standard tank drive with Omni wheels, the force generated pulling against a fixed object was 67.18 newtons. If there are only 2 wheels on the standard tank drive with Omni wheels, the force generated was 38.04 newtons. The force generated by 2 motors was 57% of what was generated by 4 motors. This deviated from what we would have predicted somewhat in that we thought 2 motors would generate only 50% as many newtons as 4. The numbers are in the right ballpark, but I'm not sure how to explain the deviation. The H drive generated 59.08 newtons, and the mechanism-based drive generated 57.68 newtons. Lastly, the X drive generated 45.85 newtons. First, let's go over how the numbers were obtained, then talk further about their deviations from idealized predictions. Here we used a Nextech model DFS 100 force gauge attached to the field border structure. A bar was then rested on the base of the hook, and the drive was then run with all motors at 100% for 10 seconds. The force gauge recorded the highest reading. 10 readings were taken for each drive design, being careful to recreate the starting positions each time. New batteries were used for each set of 10 sets. All motors had a green cartridge providing factory stated 1.05 Newton meters of torque. The equation to determine the force of the motors for the standard drive and the mechanism drive is 4 times the torque divided by the radius of the wheels. For the X drive, there is a root 2 in the denominator because the motors are not pulling in the direction that the force is being measured. Using these equations, one would expect the mechanism and standard tank drive omni wheels to have similar force generation, but in fact the mechanism drive only generates 86% of the force of the standard drive. This is likely due to the increased friction of the mechanism wheels, and possibly because some of the force of the mechanism wheels pushes into or away from the drive and not directly forward. The H drive has slightly less force generated compared to the standard drive. Specifically, the H drive generated 88% of the standard drive. This is likely due to the extra force to push the center wheel, and that each wheel attempting to push forward has less contact against the surface of the mat. Lastly, the X drive generated 68.2% of the standard drive. This is close to the predicted value, as the equations predict the X drive will generate 70.7% of the force of the standard drive. If you use the 1.05 Newton meters and the 2-inch radius of the wheels, and obviously adjust for units, the predicted newtons of force for the standard drive should be 84 newtons, and for the X drive should be 56 newtons. A comparison of the predicted force and force measured shows a 20% drop-off. This finding either has logical physics rationale or represents some consistent error. If it's of any use, the coefficient of friction of the 4-inch omni wheel against the foam mat, as posted by Technic3K on the VEX forum, is 1.3. The last aspect of the drives that we looked at was turning. This was easily the most difficult comparison to make. We chose to make the turning a very basic stepped turning program using an internal sensor. The turn would be at 75% power for the first 30 degrees, 25% power for the next 30 degrees, and lastly 5% for the last 30 degrees. Another option was to optimize turning for each drive and then compare them. The problem with this is that we would be comparing our ability to optimize turning and the ability for each drive to turn at the same time. This is why we chose a very basic means of turning. The variables that we recorded were how long it took to turn 90 degrees and how much deviation from the starting point the frame moved in the XY direction. To be more specific, the robot turned 90 degrees 4 times and then recorded the time for each 90-degree turn. After the 4 turns, the distance from where one corner of the chassis started to where it ended was measured. This process was repeated 10 times. So we have an average of the times of 40 90-degree turns and the XY translation of 10 full 360-degree turns. So here are the numbers. For turning under this possibly peculiar measurement system, the X drive performed best. In terms of time, a 90-degree turn took 1.68 seconds and only deviated 1.61 centimeters in the XY translation. The H drive, 2-motor standard tank, and 4-motor standard tank did similarly in terms of time, ranging from 1.69 to 1.82 seconds. The mechanism drive was much slower at turning under these conditions, taking 3.36 seconds to turn. For XY translation, the mechanism drive and H drive performed similarly to the X drive, but not quite as good. The translation for the mechanism drive was 2.95 centimeters, and the translation for the H drive was 3.86 centimeters. For the 2 and 4 motor standard tank drive, there was much more translation. The 2-motor standard tank had 9.08 centimeters of translation, and the 4 motor had 8.74 centimeters of translation. Our interpretation of the data is that the X drive is superior for turning. This makes sense since all the wheels are aligned for turning. In summary, if your team's goal is to thrive in the skills portion of the competition, the X drive offers more speed and possibly better turning. If your team would like to make and win finals and be named tournament champion, possibly a standard tank drive is better. Perhaps the greatest benefit that this study provides is demonstrating some absolute numbers for comparison. It would be great if others could corroborate these findings, but fair warning, it's a bit of a time commitment. What would also be useful is, assuming these numbers are accurate, hearing some elaboration for the reasons why some of the numbers deviated from what the equations predicted. The differences, although significant and demonstrable, can probably be overcome by good programming and good driving. Good luck to all teams, and we hope this helped you find your ideal tipping point.